How are you all doing this morning? Good. Good deal. We are going to be talking about the laws that govern our circuit analysis, specifically Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. So let's start by talking about Ohm's law. Way back in 1827, a German physicist named George Simon Ohm published a book entitled The Galvanic Circuit Investigated Mathematically. And in this book, he stated that the electromotive force acting between the extremities of any part of a circuit is the product of the strength of the current and the resistance of that part of the circuit. So that probably sounds like a lot of gobbledygook, but it's actually very, very important. This statement implies a directly proportional relationship between the current flowing through a circuit element and the voltage observed across the circuit element. The constant of proportionality between the voltage and the current is known as the resistance R of the circuit element. And from this, we can write Ohm's law as the voltage drop V is equal to the current I times that constant of proportionality, R, or V is equal to IR, which is exactly how you guys learned Ohm's law back in your Engineering 120 series. Now we're going to get into a little bit more depth about what Ohm's law is and how it can be applied. So let's say that I have a black box network. Okay. We're going to use this concept of a black box network throughout this class. What a black box network is a collection of circuit components where we don't know what their values are, whether they're capacitors, resistors, inductors, etc. So let's just take a generic black box network made entirely of linear circuit components, and we'll talk about what linear circuit components means next week. And we're going to apply some test voltage, which I'm going to call V test, across a pair of terminals of this black box network. We would be able to measure some voltage V across the terminals of our black box network, and we could measure some current I flowing into our black box network, and the resistance of whatever is inside this black box network is simply the ratio of V divided by I. This is kind of an experimental method for us to be able to determine resistance, and we are going to use it in certain instances a bit later on in the class where we have to come up with, I would say, creative methods for determining the resistance of a given network. So from this expression, we can see that the units of resistance, which we know to be ohms from our Engineering 120 series, is fundamentally the same as 1 volt per amp, okay? And I'm going to define resistance as well. So resistance is a measure of how difficult it is to pass current through a circuit element. So elements with high resistance mean that it's difficult to pass a lot of current through them, and elements with low resistance means that it's particularly easy to pass a lot of current through them. Now, the resistance of a conducting medium is defined also by the geometry of the conductor and the material from which it's made. So you may recall from Engineering 121 that there was an equation for resistance. R is equal to rho L over A, okay? Where rho is the resistivity of a material, L is its length, and A is its cross-sectional area. So, for example, if I had a bar of a certain type of material, like so, and I was attempting to pass current into this front face and have it come out of this back face, the resistance of this bar would depend on this dimension, which is the length of the bar, as well as the cross-sectional area of the bar, which is the face that the current is flowing into, as well as the material that the bar is made of. So I would see a particular resistance if I pass the current in this direction, but if I pass the current through the bar in this way, so through that top face and then coming out the bottom, I'm just going to call this I2, the bar would exhibit a different resistance. Everybody understand that. And the reason being is that it has a different length. So in the second case, our length would be this dimension, and our area would be the surface area of that top. I'm bringing all of this up because I want to determine what the resistance of a wire is, okay? So let's say that I have a wire. We know, generally speaking, we'll consider a wire to be a cylinder. Like so. Let's say that it has a length of 10 meters. It has a diameter of 1.024 millimeters, and it is made of copper, where copper has a resistivity of 1.68 times 10 to the minus 8 ohm meters. And we are going to assume that it works like any wire we've ever seen before, wherein current is flowing into one end of the wire and it's exiting the other end. Okay. This particular wire, or a wire with these dimensions, is what is known as AWG, or American Wire Gauge number 18 copper wire. This is wire that's a little bit larger than the wire that came in your kits in the Engineering 120 series, okay? If we wanted to figure out what the resistance of a 10-meter long section of wire was, we could simply plug these dimensions effectively into our equation. So for instance, we would know that the resistance is the resistivity, which is 1.68 times 10 to the negative 8 ohm meters, times our length, which is 10 meters, divided by pi over 4 multiplied by the diameter squared. 1.024 times 10 to the minus 3 meters quantity squared. And we would find that our section of wire, which is 10 meters long, has a resistance of 204 milliohms. Okay, so let's talk about that real quick. How long is 10 meters of wire compared to the lengths of wire that we used in the Engineering 120 series to wire up a simple circuit?
Very, very long.
Yeah, so typically speaking, we might have a couple of inches, which would translate to probably at most 5 to 10 centimeters worth of wire length for anything that we did. At least in 120 and 121, you might have used longer wires if you needed them in your prototype for Engineering 122. But typically speaking, we wouldn't be anywhere near the length of 10 meters because that would be something close to, I think, 35 feet or somewhere around there, maybe 31, 32 feet. So quite a lot of wire, okay? Now the resistance of a 10-meter long length of AWG 18 wire is about 1/5 of an ohm. How does that compare to the size of the resistors that you used in, say, the Engineering 120 series? Anybody remember any of the resistor values that you happen to use?
We had some values as high as 10,000 ohms when we wanted to save current in some circuits, and some as low as 220 ohms, 240, all of those values. So there was a range.
Yeah, so the smallest resistor that you guys used, I believe, was around 200 ohms. And you use that in an LED circuit in order to limit the current in the LED circuit, but make the LED shine as brightly as possible. So that, let's call it a 200 ohm resistor, is actually 1,000 times larger than the resistance of this particular 10-meter long section of wire. Now, the reason why I'm harping on all of this is because if I draw a circuit, let's say that I have some voltage source having a voltage Vs, and I connect it to some circuit element A, and in turn, element A is connected to some circuit element B. I connect my voltage source to element A and potentially element A to element B using wires in any practical circuit, right? Well, let's say that element A and element B were resistors.
Dr. Hartman, I have a question.
Yes.
For the calculation of R above, shouldn't the answer be ohms? And shouldn't that 204 be 0.204 ohms instead of 204?
So it's 204 milliohms or 204.
Oh, okay, I see. I thought that was a meter because the M.
0.04 ohms, And I am saying that my answer is exactly the same. Right? Because milli means times 10 to the minus 3. So we're both right.
The M looked like a meter, ohm meter for some reason. That's why I thought.
Oh, okay. So when I have a compound unit, like an ohm times a meter, I usually put a center dot to indicate that there is multiplication of units.
Okay.
Right. So okay, I understand where the confusion was, and thank you for pointing that out. Right. So that is not a meter times an ohm. That is a milliohm. Whenever I have an ohm meter, like I said, I will put the ohm symbol and then a dot indicating multiplication, and then the M for meter. But thank you. That's was probably confusing to other people as well.
Yeah, thank you.
So I have, let's say, some resistance RA, don't really know what it is, and some resistance RB. Based on our experience, the resistance of resistor A and resistor B is probably a lot higher than the resistance of the wire that's connecting things in our circuit, okay? So in engineering 120 and 121 and all that kind of stuff, we made an assumption that the resistance of a piece of wire is effectively 0, and we've just mathematically proven why that is, or why we can neglect the resistance of wires. Now, that won't always be true. In the overwhelming majority of circuits that we're going to deal with in this class, we are going to treat wires as having 0 resistance. But there are some applications, particularly in high power applications, like setting up systems to feed motors and HVAC units and stuff like that, where the resistance of the wire is actually important enough to merit determining it and including that in our calculations. I will tell you explicitly when we're going to be using the resistance of a wire, and typically I'll just give it to you and say the resistance of the wire is X, but I just wanted to point that out. So that actually brings us to another little side topic that I want to talk about. There are 2 common terms that you may have heard that I'm going to define that have something to do with resistance, okay? The first is the concept of a short circuit. So in our class, a short circuit would mean if I have a set of terminals and I place a wire directly between those terminals, this is a short. It has a resistance of 0 ohms, which means the voltage drop across this short is exactly equal to 0 volts because of Ohm's law. And any amount of current that needs to flow through that short circuit can flow through that short circuit, okay? So anywhere that we have a wire, we have a short circuit. The opposite case is an open circuit, all right? So if I have a pair of terminals like so, and there is no connection between them, then that means that the current flowing between that set of terminals is exactly 0, which implies that there is a resistance of infinity ohms there. These representations of short circuits and open circuits will be very, very useful once we get to a concept called superposition. But for now, I just want to be very, very clear. Whenever we're talking about a short circuit, we have a 0 ohm resistance, and we know that no voltage drop occurs over the short circuit. Whenever we have an open circuit, the resistance is infinitely large and no current can flow through the open circuit. Okay. So with that out of the way, we can develop some other relationships around Ohm's law. So we know that Ohm's law gives us V is equal to I times R, and we also know that power is equal to I times V. So if we substitute in this relationship, if we substitute in our Ohm's law relationship into our power relationship, we can actually get two new expressions. The first of which is I squared times R, which allows us to calculate the power absorbed by a resistor if we only know the current flowing through it. And our second equation is V squared over R, which allows us to calculate the power absorbed by a resistor when we only know the voltage drop over it. Now, I've said in both of these examples that we are going to be calculating the power absorbed by the resistor. So I would like to talk a minute about why we will never calculate the power that is supplied by a resistor, okay? So the first explanation for why we can never calculate the power supplied by a resistor is actually fairly simple. If the current flowing through the resistor is negative, when we square it, we're still going to get a positive number, right? So I squared times R, regardless of the sign of I, will always be positive. And from our passive sign convention, that means we will always be absorbing power. Similarly, the voltage is squared as well. So regardless of the polarity of our voltage drop over a resistor, the resistor will always be absorbing power. Now, there is a physics-based reason for why a resistor can only absorb power as well, and it's all about what a resistor does, okay, and how a resistor behaves. So let me draw another simple picture of a bar of material here. All right, so let's consider that this was a piece of resistive material where we had a lead, or some sort of wire in one end that allows us to pass current through, and a wire coming out the back end where that's our current path, okay? So what's happening is that inside of this bar, there are atoms, because there are atoms in everything, right? And these atoms all throughout this bar, and what these atoms do is cause what are called scattering events. And so what that means is that, let's say an electron is trying to pass through this bar, it bounces off this atom and has to turn around, and it follows a very weird, jagged, bouncing around path all the way through until it reaches the opposite end of the bar. Well, every time any of these electrons hit one of these atoms within the structure of the resistor, it generates heat, okay? And so that generation of heat is how the resistor absorbs energy, okay? So a resistor, all it really does is converts electrical energy into heat. It can never store energy because it has no means by which to store it, which means it can never supply energy either. All it can ever do is convert electrical energy into heat. So you guys may not be fully aware of this, but if you or your parents own an electric stove or something like that, the heating elements of your stove, and I'm going to draw a terrible representation of one. So the heating element on your stove might look something, like this. And I'm trying to figure out how to draw that it's coming out of the other end. Anybody know why they have this coil-based shape? Any thoughts? Any guesses?
Maybe to increase the length so the resistance is higher.
That is exactly correct. That is literally why they are shaped the way they are shaped. It's to make those pieces of material that are resistive as long as possible so that the resistance is higher. That way you can apply a smaller voltage to generate the most amount of heat out of this thing. That's also the reason why what's called nichrome wire is used in space heaters. It is a particular type of wire that has a much, much higher resistance than, say, copper or something else. And it's also mechanically very stable as well, so that you can pass a current through it and it'll glow red hot and generate heat, which is then blown off of that wire using a little bitty fan. And that's how electric heaters work. So all of these things, most of the applications of directly using a resistance in our current society are all about converting electrical energy into heat. What we use them for in engineering 120 and stuff like that, the generation of heat is really a byproduct. They were used to limit current, and they do that by converting the electrical energy stored in the current into heat. All right, so I now want to talk about the concept of conductance. All right. So if we look back at this original black box network here, the constant of proportionality between the voltage and the current is known as the resistance. But we can actually define it in a different way, right? So if we have a black box network, we apply a test voltage. We measure some voltage across the terminals of the network. We measure the current flowing into the network. We can get a second constant of proportionality, G, where G is what's known as the conductance of the material, okay? And conductance is simply the ratio of the current divided by the voltage, which means it is exactly the same as 1 over the resistance. Conductance has units of Siemens, which is fundamentally 1 amp per volt. Now, I want to talk very briefly about conductance before we develop a couple of more expressions for it, okay? Conductance, I guess I should define it as well, just real quickly. Conductance is a measure of how easily or how easy it is to pass current through a circuit element. All right, so we are going to talk about conductance in this class literally right now, and that's about it. And the reason for that is I've taken oodles and oodles of electrical engineering classes. And the only time that I dealt with conductance, other than the simple definition of it way back when I took Circuits 1 in, gosh, 2009 or, oh, actually, no, 2006 or something like that, was in my transmission line theory courses, where conductance was used to model current leakage between conductors in a parallel transmission line. So it really doesn't have much application for general electrical engineering purposes. And so I don't really feel that it's appropriate to spend a whole heck of a lot of time talking about it. Now, unfortunately, the person who made out the web work assignments absolutely does want you to pay a lot of attention to conductance, at least for the particular homework assignment that goes along with this lecture. I would highly encourage you, anytime you're dealing with a conductance, to simply convert it into a resistance and then move along with your life. That will be the much easier way to handle the concept of conductance for the overwhelming majority of problems you will ever face with it. Okay, so I just want to be very clear about that. Let's introduce very quickly the schematic diagram symbols for resistance and conductance as well. And this can be potentially a little bit confusing. Here is the symbol for a resistor. And here is the convention. Voltage flows, the voltage drop across it is this way with a positive polarity terminal on the left. Then the current I needs to be flowing into the positive polarity terminal. Then we know that V is equal to I times R. If, and that's from Ohm's law, if we have a resistor whose value is R, and our voltage drop across our resistor has the opposite polarity, so negative polarity on the left, while the current I is flowing into the negative polarity terminal, the voltage drop across the resistor is negative I times R. And this is because, as I stated previously, a resistor can only absorb power. So this convention forces our resistor to always be absorbing power. So if the current is flowing into the positive polarity terminal, the voltage is I times R. If the current is flowing into the negative polarity terminal, the voltage is negative I times R. This will show up on a multitude of homework problems and stuff like that. So I just wanted to point it out specifically. Now, let's show you the symbol for conductance. It is literally the exact same symbol, but it would have a magnitude of some number measured in Siemens. That is the only way you can tell a conductance from a resistance in a circuit diagram, is if it's listed as being, 14 Siemens as opposed to some number of ohms. It obeys the exact same principles. So if we have current flowing into the positive polarity terminal, then let's see, V is equal to I. Oh goodness, what that just happened there? Actually, let me do it the other way. I is equal to V times G for a conductance in which current is flowing into the negative polarity terminal. Current is equal to negative V times G. Okay, so I really think that's enough out of me with regards to Ohm's law. Does anybody have any questions regarding Ohm's law, resistance, or conductance? All right, nobody's saying much of anything, so let's move along. Our next topic that we're going to talk about is Kirchhoff's voltage law. All right. So let's say that I have a simple circuit containing only voltage sources and resistors. I'm going to call this guy VS. Let's call this guy R1, R2, and I'm going to change this from VS to VX. I just decided to use two different voltage sources. So this will be VX and this will be VY. And let's call this guy down here R3. Now you may recall from our last lecture that we said that the voltage between 2 points, VBA, was equal to the line integral from A to B of the electric field dotted into some differential line element. And we also express this as 1 over Q times the integral from A to B of our electrostatic force, Fe, dotted into some differential line element. Now, the electrostatic force is a conservative force. So, what that means is that if I do a closed line integral around the entire path of a circuit of either the electric field dotted into dl or the electrostatic force dotted into dl, I should find that the total voltage drop around this closed path is 0. Okay. So let me write this in a way that's probably a little bit easier to understand for you guys. Okay. I am going to arbitrarily assign voltage drops to my resistors. Okay. So let me explain how I do this. I pick a voltage source. In this particular instance, I'm going to pick the voltage source Vx. And I'm going to say that there's going to be some current that leaves the positive polarity terminal of that voltage source, Vx. I'm going to call this guy I. Because I know that my resistors need to be absorbing power, I'm going to arbitrarily choose a polarity for the voltage drop across that resistor, because Ohm's law tells me that if I have current flowing through a resistor, I should expect to have a voltage drop. So I'm going to say that the voltage drop across resistor R1, which I'm calling V1, has the positive polarity terminal on the left-hand side, so that that current I is flowing into the positive polarity terminal. Is everybody catching what I'm throwing here with regards to how I'm assigning things? All right, nobody's saying much anything, so I'll assume I'm good to go. There's going to be a voltage drop over that resistor R2, and I want the current to flow into the positive polarity terminal. So that means I place the positive polarity terminal on the left. And then I'm going to have some voltage drop over this resistor R3, and the positive polarity terminal should go on the right, because my current, as it makes its clockwise path around this circuit, will be flowing in from the right-hand side and exiting the left-hand side. So Kirchhoff's voltage law tells me that if I start here at the bottom left-hand corner and I follow my current around this path and wind up at the bottom right-hand corner, I can develop a relationship, okay? So for this particular example, my Kirchhoff's voltage law equation should be negative Vx. And the reason why it's negative is because as I follow I around, I see the negative polarity terminal of that voltage source Vx first, plus V1, plus V2, plus Vy, plus V3 is equal to 0. Now, if I knew what my resistor values were, I could actually use an equation like this to solve for my unknown current I. And that is exactly what we are going to do here. But because I am me, we are going to make it a little more difficult. So let's say that I have the following circuit. Where I have a 120 volt source. I have a 30 ohm resistor. I have a dependent source giving me a voltage of twice VA. And I have a 15 ohm resistor like so, where VA is defined to be the voltage drop across the 15 ohm resistor with a positive polarity on bottom. My ultimate goal in this particular problem is to determine the power absorbed by my dependent source. Okay. So I would like some input from you guys on how you think we might go about solving a circuit like this. This is probably, it looks fairly straightforward, and to be honest, it is, but the dependent source in this circuit makes it arguably more difficult than literally anything you did in engineering 120, 121, etc. So we're setting the bar kind of high here. So let's talk about what we can do. Anybody have any thoughts? All right, nobody's, oh, sorry, go ahead.
No, I really have no idea. I just didn't want to, leave you hanging. I don't know what to do.
All right, well, I
when I-
appreciate that. What is, sorry, somebody else was saying something. What's up?
Also, I think if we do the KVL, we'll find VA, and then we plug in VA into the dependent source, then we get the voltage there. And I think we will find the current going through the loop, then multiply the voltage we found for VA times 2A, and then get the voltage, then times that by the current to get the power going through the dependent source. Would that work?
Okay. Yeah, so let's take what Mr. Elijah's suggestion is. We're going to break this problem down into digestible steps, okay? So we know that the power absorbed by the dependent source, hopefully we know this anyway, is the voltage drop across the dependent source multiplied by the current flowing through the dependent source. And whether or not we need a positive sign or a negative sign depends on how we define the current, okay? And technically how we define the polarity of the voltage drop across our dependent source. So the first thing that I'm going to do here, and this is pretty obvious, I'm going to say that the voltage drop across my dependent source is VDEP, and it has the polarity, positive polarity on the left, negative polarity on the right. And the reason why I chose that is so that it is the exact same as the polarity that is associated with the source itself, okay? So we can see pretty easily that V dependent is simply twice VA. Is everybody okay with that?
Yes.
Yeah, well, hopefully that part at least makes sense, okay? Now, because I am trying to find the power supplied by my dependent source, I am going to choose to make I dependent have a direction such that it is flowing into the positive polarity terminal. So I'm saying that I dependent is the current that's flowing around this loop. Does anybody have any problem with me choosing I dependent as flowing around this loop in a clockwise direction? We could just as easily do it negative clockwise, or excuse me, counterclockwise or anti-clockwise. It's just going to result in more negative signs for us to have to keep track of. So if I have assumed I dependent to be flowing around in that direction, my next step would be to write a Kirchhoff's voltage law equation. Okay, so I'm going to start in the bottom left-hand corner, and I'm going to follow my current around the loop. So I see negative 120 volts plus, I'm going to go ahead and just write this real quick here. It's the only really unknown voltage that I have, so I'm going to call this guy V30, positive polarity on the left, negative polarity on the right. So plus V30 plus V dependent, and then minus VA is equal to 0. And there's a simplification that I can make that I'll go ahead and do right now. So my negative 120 volts is going to stay. My V30 is going to stay. But I could say that V dependent is twice VA. And then from that, I have minus VA. So this is going to look like now plus VA is equal to 0. Is everybody okay with that simplification?
Yes, sir.
Okay, if I need to break it down literally tiny step by tiny step, I'm happy to do it. But if we can go with this, then that's fine. All right. So now we have one equation, but we have two unknowns. V30 and VA are both unknown quantities. So what we're going to do is we're going to use Ohm's law to express that voltage V30 and that voltage VA in terms of our current I dependent, because that same current flows through every element. So we can effectively eliminate variables by putting everything in terms of one variable that's common to the entire circuit. So using Ohm's law, and I'll do it over here, what is the relationship between V30, the 30 ohm resistor, and the current I dependent?
it's I dependent times 30 ohms.
I dependent times 30 ohms, okay? That's absolutely correct. The current is flowing into the positive polarity terminal, so it should just be I dependent times the resistor value of 30 ohms. Now, what about the relationship between VA, I dependent, and the 15 ohm resistor?
Is it going to be negative I dependent times 15 ohms?
That's exactly correct. Negative I dependent times 15 ohms, where the negative sign is coming from the fact that the current is flowing into the negative polarity terminal, okay? So if we substitute both of these relationships in, I'm going to rearrange ever so slightly by putting the 120 volts on its own on the right-hand side here, okay? So I have V30, which is 30 ohms times I dependent, plus VA, where VA is negative 15 ohms times I dependent. And I can group like terms, right? So 30 minus 15 gives me 15 ohms times I dependent is equal to 120 volts, which means I dependent is 120 volts over 15 ohms is 8 amps. Does anybody have any problem with the algebra that I've just done there? All right, nobody's saying much of everything or anything, so I will say that I'm correct. So we figured out what I dependent is. We know that it's going to be 8 amps. How would we figure out what VA is? Because in order to get V dependent, we need to know what VA is.
Current times resistance.
Yeah, I mean, we have, let's see what's going on in the chat here. Yeah, negative 8 times 15. So we have an equation for VA literally written right here. We just used it a moment ago. So we can substitute in I dependent into that. So we would have negative 8 amps times 15 ohms, which should be negative 120 volts, right? So twice VA is going to be negative 240 volts. Everybody okay with that? All right, nobody saying much of anything. So when I multiply these two guys together, 240 times 8, I believe I get 1,920, but let me get my calculator out just to make sure. Negative 1,920 watts. So this is the power absorbed by my dependent source. So somebody tell me what the power supplied by my dependent source is.
Positive 1920.
Exactly right. So if it's absorbing negative 1920 watts, it's supplying positive 1920 watts. I just want you guys to pay attention to that simple relationship. Okay. So this was a pretty, I don't want to call it complicated because I really don't feel like it was, but I think it's a pretty representative example, let's say, of maybe a hard-ish question I might ask on an exam. It's an example of what's called a single loop circuit. In a single loop circuit, there's only one current flowing around the loop, so that's what helped aid our analysis. I want to look at another example where we can apply Kirchhoff's voltage law, and this is one that I'm doing to introduce the concept that some students have difficulty understanding. Okay. So let's say that I have the following circuit. Our goal in this circuit is to determine the value of Vx and to determine the value of Vy. Now, the thing that trips up most students when they look at something like this is really about how to correctly apply Kirchhoff's voltage law and when we can apply it, okay? And one of the biggest things that is confusing to people is what I mean by this bit right here, okay? I have a 12-volt drop, let's call it in the middle of my circuit, and a lot of students get confused by what this means. And it all boils down to the fundamental definition of voltage, where voltage is defined as a potential difference between two points or nodes in a circuit. So if I have a 12-volt potential difference where I just had boxed in red, that means that this node I'm outlining in pink is at a potential of 12 volts higher than this node, which I've just outlined in green. Now you may asking yourself, or maybe asking yourself, well, how does that little bit of information help? Okay. I'm going to write a Kirchhoff's voltage law loop, but I'm going to show you exactly what loop that I'm referring to. Let me do it in orange. Okay. So I'm going to start right here. Go over here and then come down across this gap and then come back this way. So I start and I end at the same point, okay? So my Kirchhoff's voltage law equation for this first loop, I'm going to call it loop 1, would be negative Vx plus 12 volts minus 6 volts is equal to 0. And I can easily solve this and then say that Vx is equal to 6 volts. The math isn't the hard part to understand here. What most people or most students seem to not understand is why I can do this bit right here, right? And the reason is because I'm applying Kirchhoff's voltage law. Okay, so I guess the fundamental misunderstanding here is that when I'm writing an equation for Kirchhoff's voltage law, they expect that I have to write it around a closed loop, meaning that all of the different parts of my Kirchhoff's voltage law equation have to be capable of carrying current. And I would like to emphatically argue that that isn't the case, because Kirchhoff's voltage law says if I add up all of the voltages and I start and end at the same point, regardless of the path I take, the sum of those voltages has to be 0. So it doesn't matter that I take a voltage drop over this open circuit in the middle of the circuit. If I know what the voltage drop across that open circuit is, it's absolutely fair game. Does that make any sense to you guys?
Yes, sir.
Okay. So figure out what or how to determine Vy. What would be a good loop or Kirchhoff's voltage law loop, I guess, to take? Any thoughts?
Could you just go around that top loop?
So I could go around the top loop. So I'm going to assume you mean this guy that I'm outlining in gray. Is that what you're referring to?
Yeah.
So I have a small problem with that loop. Okay, but let's write it out. Let's call this loop 2. And we'll see what we're running into. All right. So if I do it around that top loop, starting at the bottom left-hand corner, which is where I typically start things, I'm going to have negative Vx, which I know to be 6 volts. So I'm just going to call it negative 6 volts plus Vy. And then I have that resistor, this guy right here, which doesn't have a known voltage drop over it. So how do I take that into account in my equation?
You gotta use Ohm's law.
Okay, if I were to use Ohm's law, how would I do that when I'm not told what the resistor value is?
Yeah, that's true.
Yeah, you
And we don't
can.
know what the current is.
Yeah, we don't know what the current is. We don't know what the resistor value is, either of those. So I would argue that going around loop 2, or as we've defined it there, is maybe not the best idea. So let's take another guess. What if I went around this loop? does this loop, I'm going to call this one loop 2 again, that I've outlined in brown, if I follow this loop, is there any unknown voltage other than Vy?
No.
All right, I agree with that statement. And I'm going to ask you guys to tell me what my Kirchhoff's voltage law equation should be, okay? So I'm starting here at this point that I've labeled in brown, and I'm going to follow that loop around its clockwise path. So somebody tell me what my first term should be.
-6 volts.
All right, so -6 volts. What comes next?
-12 volts.
There we go. What's next?
Plus Vy.
All right, and then my last term,
Plus 4 volts.
plus 4 volts, and set this equal to 0. And I can then solve this guy and find that Vy is equal to 18 minus 4 is 14 volts. So the purpose of this example really was twofold. A, to let you know that you can absolutely do Kirchhoff's voltage law across open circuits if necessary. And B, to get you in the habit of trying to form Kirchhoff's voltage law equations where the path that you're taking to form your Kcl equation has the least that's going to help you get to the final answer more quickly. So that original gray path that we took, we could have actually used that by assigning another variable voltage to that particular resistor and then using another KVL loop to figure out what that voltage is and then substituting it back in. But again, that's not the quickest or most efficient path, so that's why I discouraged us doing it. All right, before we move on to our final topic for the day, which is Kirchhoff's current law, does anybody have any questions about Kirchhoff's voltage law and how to apply it? We're going to be using Kirchhoff's voltage law is effectively fundamental to circuit analysis. One thing that I don't think I mentioned before, but hopefully it'll make a little bit of sense. Kirchhoff's voltage law is the law of conservation of energy in circuits form, okay? What I mean by that is we know that voltage is by definition the amount of work it requires to move electrical charge around a circuit. So it should make sense that it should take no work at all in total to move charge from, say, this point at the bottom left-hand corner of the circuit back to the bottom left-hand corner of the circuit. If it took work to move it from here to here, we would not be dealing with a conservative system, and therefore effectively the law of conservation of energy would not be valid because all of the energy transferred moving that charge wouldn't cancel each other out. All right, let's talk now about Kirchhoff's current law. I'm going to start by drawing a fairly simple circuit. I'm going to say that the amount of current that's flowing through element A, I'm going to call that current IA, and the amount of current that flows through element B, I'm going to say is IB. What is the relationship between the current IA and the current IB? Can anybody tell me?
They should be the exact same.
They should be the same. So our assumption here is that IA is equal to IB. Why do you say that?
Because they're connected in series.
Okay, so because they're connected in series. I like that answer, but I like a little bit more general answer as well. So I'm going to look at this node point right here, okay, in between elements A and B. So it stands to reason that if the amount of current that's flowing into element A is IA, then the amount of current that's flowing out must also be IA, right? The same amount of current has to flow in to the element as flows out. This is fundamental to electrical engineering, and that is because of the law of conservation of charge. If more charge flowed in than flowed out, then that means that element A would be destroying charge, which we know can't be true. And similarly, if more current flowed out than flowed in, then that means more charge is flowing out than is flowing in, which means charge is being created by element A, which would also violate the law of conservation of charge. So the current flowing into the top terminal of element A has to be the exact same current flowing through the bottom terminal of element A. And similarly, the current flowing into the top terminal of element B has to be the current flowing out of the bottom terminal of element B. So we can see that current IA is flowing into that node point and current IB is flowing out of that node point. And the argument is that those currents are equal because the two elements are connected in series. That is true, but I would argue that the reason that those two currents are equal is because the current has nowhere else to go, right? How could they not be equal? There's no other possible path for the current to take. So we can view this perspective as the current flowing into a node has to equal the current flowing out of a node. This sentence is more commonly known as Kirchhoff's current law. Okay. So I believe that is exactly how you guys learned it, or at least that sentence is how you learned it way back in Engineering 120. Okay, we're going to use the exact same thing here, but with a couple of other little caveats. All right. So I'm going to draw a node. And that doesn't connect, so that's not going to be good. And I'm going to draw several paths that are trying to connect to this node. And I'm going to assign each one of these paths a current. So let's call this guy I1, this guy I2, this guy I3, this guy I4, and this guy I5. If we use the representation of Kirchhoff's current law that we just described, the current flowing into a node has to equal the current flowing out of a node. We can write what's called a Kcl equation, which would be the current flowing in, I1, plus I4, has to equal the total current flowing out, which is I2 plus I3 plus I5. Does anybody have any problems with that mathematical relationship?
No, sir.
All right. A second way to look at Kirchhoff's current law is to treat all of the current as flowing into the node. So in that way, we could say that flowing into a node is equal to 0. So let me mathematically explain what I mean by this sentiment using these exact same relationships, okay? So the current I1, we can easily see is flowing into the node, right? Now the current I2 appears to be flowing out, which is the same as saying that negative I2 is flowing in. Similarly, negative I3 is flowing in, positive I4 is flowing in, and negative I5 is flowing in. And the sum of all of these has to be equal to 0. This is the exact same mathematical expression that we would get if we took the right-hand side of this equation and moved it over to the left-hand side. There is a third representation of Kirchhoff's current law that says the total current flowing out of a node equal to 0, where we could say that negative I1 flows out, positive I2 flows out, positive I3 flows out, negative I4 flows out, and positive I5 flows out. This is the exact same thing as our expression we gained from number 2, but just multiplying both sides by -1. So we're looking at it from a slightly different perspective. All three of these methods of approaching Kirchhoff's current law are valid because they all exactly represent the same thing, just from a slightly different perspective. So I say that because for right now, the overwhelming majority of you are probably much more comfortable with our first definition. Current flowing in has to equal the current flowing out. There's nothing remotely wrong with this whatsoever. However, when we introduce the concept of nodal analysis next week, you'll find that approaching KCL using our third option here that says the total current flowing out of a node is equal to 0 will probably make much more sense and make our analysis more simple and standard to carry out. Okay, so I'm introducing all three of them. You were perfectly fine using whichever one makes the most sense to you. But once we get to nodal analysis, I am going to be using representation number 3 of Kirchhoff's current law pretty much every single time because it makes the equations easier to generate and easier to follow. All right, so let's put Kirchhoff's current law in action. I'm going to have a fairly complicated circuit because, again, that's just who I am. And we are going to work our way through it. So I'm going to define a few variables. Here is Vx. Here is Ix. And here is how I will define Iy. And our ultimate goal in this particular problem is to determine Vx, Ix, and Iy using some combination of Kirchhoff's current law and Ohm's law. Okay, so I'm going to tell you guys exactly how I intend to start this problem out. Okay, so when we're applying Kirchhoff's current law, we need to pick a node at which to apply it. So I am going to pick the top node. And I am going to assume a convention. And the convention that I am assuming, and I'll explain this momentarily, is that currents leaving the top node will be considered positive. So really what that is me applying method number 3 or definition number 3 to Kirchhoff's current law. All right. So I'm going to start at the left-hand side of my node, and I'm going to start writing equations. Okay. So I'm looking for the current that is flowing down through my 6 kilo ohm resistor. All right. There are a couple of different ways that I can express it, but I'm going to start with something simple and just add currents together. All right. So I'm going to say that the current flowing down through my 6 kilo ohm resistor is negative Ix. Does that make sense to you all? Let's start there.
Explain why it's a negative real quick for me.
Okay. So the current Ix, we could say originates here at the bottom terminal of our 6 kilo ohm resistor and then flows up and then turns right at that corner, which gives us the same direction as we see how it was defined. Does that make sense?
Yeah.
So the red arrow that I've drawn, which is what I'm considering to be the positive current leaving that topmost node, is of the opposite direction as my current Ix, which is why I'm saying it is representative of negative Ix. Make sense?
Yeah, I got it now.
Okay, so thank you for the question, because I guarantee you there were other people that were like, where the hell did he get negative Ix from? So thank you for being brave enough to ask. All right, so what about this current through this branch? What is that going to be? Where I'm assuming that if it were flowing down, it would be positive.
Should it be -6 milliamps?
That's absolutely correct. -6 milliamps. What about the next branch with the dependent current source?
Positive 4ix.
Absolutely correct. Positive 4 Ix. All right. Now this next one is a little tricky. All right. We're talking about the current that's flowing down through the 2 kilo ohm resistor, but we haven't defined it as a current or anything like that. Now, we can associate that current with one of our variables. Let's see what's going on in chat here. All right, so the question is, why is it positive 4 Ix? All right, Mr. Wills, so the reason it's positive 4 Ix, let me get a different color here, is because this arrow associated with the current source is in the exact same direction as the arrow where we're, for our convention, that's telling us which direction is positive. So because the arrows are pointing in the same direction, it's positive 4 Ix. When the arrows were pointing in the opposite directions, which is what we had here, that's why we had -6 milliamps. Okay, fantastic. It's over here. So this 2 kilo ohm resistor is going to be a little bit tricky. And so I am going to argue that it will be easiest to use Ohm's law to develop a relationship for it, okay? Now, the reason why I say that is because while we don't know what the voltage drop over that particular resistor is, like we don't have a numerical value for it or anything like that, we do have a variable that already describes it, okay? So I would argue that using Ohm's law, we could say that the voltage drop, sorry, let me change color back to black. Excuse me, that the current that is flowing down through that 2 kilo ohm resistor is Vx divided by 2 kilo ohms. So let me take a moment to explain why I can say that, all right? My voltage Vx, which is defined way over there on the left-hand side of the circuit as the voltage drop over the 6 kilo ohm resistor, has the positive polarity terminal associated with the top node of the whole circuit. Similarly, the negative polarity terminal is associated with the bottom node of the whole circuit. So because everything is in parallel, Vx is the voltage drop over every circuit element in this circuit. Positive polarity on top, negative polarity on bottom. Does that make sense? It's the fundamental definition of voltage, right? It's the difference in electric potential between two nodes. So I could just as easily say that this is Vx, because it is. It's the same voltage with the exact same polarity definitions. And so using Ohm's law, where the current down is flowing into the positive polarity terminal, that means positive Vx divided by 2 kilo ohms is, sorry, this little current right here flowing down. All right. How are we going to represent the current flowing through the 2 milliamp source? Will that be positive 2 milliamps or negative 2 milliamps?
Positive.
All right. So
Positive.
guy 2 milliamps, absolutely correct. And for the current flowing down through our 3 kilo ohm resistor, how does that relate to the current IY? Will it be positive IY or negative IY?
Positive IY.
Positive IY, right? So as we follow IY around its path, it winds up flowing down through the 3 kilo ohm resistor, which is in the same direction as our reference. So plus IY is equal to 0. So we have one equation and 3 unknowns. So this is an example, again, of a single node pair circuit where everything is in parallel. And as I discussed previously, that means that every circuit element has a voltage drop of Vx over it. So we can develop a relationship to express Ix and Iy in terms of Vx. So let's start with the one that I think is a little bit easier. Using Ohm's law, we should be able to say that Iy is the voltage drop over the 3 kilo ohm resistor, which is Vx, divided by the resistance value of the 3 kilo ohm resistor, which is just 3 kilo ohms. Now, my question to you guys is, should this have a positive sign or a negative sign associated with it?
It should have a positive sign.
It should have a positive sign. That's absolutely correct. So the reason that it has a positive sign, let me go ahead and put Vx over here again for you guys, is because the current Iy, as it's defined, is flowing into the positive polarity terminal. So that means that the Vx, in this case, should be positive. For Ix, we have a voltage drop of Vx divided by a resistance of 6 kilo ohms, but we should have a negative sign because the current Ix is flowing into the negative polarity terminal of the resistor. Does that track with everything that we've done so far in this class?
Yes, sir.
All right. So if I substitute those relationships in, I can get a single equation in terms of Vx, right? So that would be, so I have negative Ix, so that's going to be negative, is Vx over 6 kilo ohms minus 6 milliamps plus 4Ix. So that's 4 times negative Vx over 6 kilo ohms plus Vx over 2 kilo ohms plus 2 milliamps plus Iy, which we know to be positive Vx over 3 kilo ohms is equal to 0. Solving this guy gives us Vx is equal to positive 12 volts. From here, we simply substitute in Vx into our equations for Ix and Iy. And so that's going to be 12 volts over 3 kilo ohms is 4 milliamps. And here we have negative 12 volts over 6 kilo ohms is negative 2 milliamps. And we're finished. We've solved for all 3 unknown quantities. Taj says, shouldn't the first term be negative Vx over 6? It should not, okay? And so let me explain why it shouldn't. Ix is negative Vx over 6 kiloohms, right? But we have negative Ix. So those two negative signs canceled each other out, giving us positive Vx over 6 kiloohms. Alrighty. So we've wrapped up 15 minutes early for today, and I think I think that's okay. I could do another example problem, but I feel like you guys are probably getting a little burned out listening to me talk. So what I would highly suggest that you do when you have the time over the next couple of days is pop onto WebWork and take a crack at some of the problems from homework set 1 and homework set 2. And if you have any questions or run into anything that doesn't make sense, kind of write a couple of things down, and we can spend a few minutes at the beginning of class on Wednesday trying to rectify those situations, because I can think of at least one problem from homework set number 2 where it can be a little bit tricky. And so I certainly wouldn't mind talking about that problem if any of you guys have any questions about it.